All right, folks, it's Bass Action back in action here. In this video, what we're going to look at is transformations that involve a horizontal dilation and a horizontal shift. And we'll also look at one example of a vertical dilation and a vertical shift. So specifically, what matters is when you're working with either horizontal or vertical, and then you have both a dilation and a shift. Some special things happen, and you've got to slow down and think about them before you jump in. So the first thing that I wanted to do is kind of lay some groundwork for some reference points for us as we work through this. So what I've done here on the left-hand side is I've started off with a function, a nice square root function that has some shifts in it, no dilations, but just some vertical and horizontal shifts. Helps kind of create a better picture for us. And what I've got here is a square root function with a horizontal shift and a vertical shift. And then I went ahead and I made the big T-chart here for. Now I certainly made a T-chart bigger than what we would normally see or need to create, but it's good for a reference. So you might want to pause and just make sure that this T-chart makes sense and that you can understand where I got the numbers and that they would in fact graph what we want it to graph. Now, the next thing that I did is I took this same function and I created a T-chart for this transformation. So the first T-chart is for this exact function, and then what I did is I transformed it to create the second T-chart. Now, the way I got that T-chart is I actually performed this transformation. So I took this entire expression here, this 2x plus 3, and I subbed it in for our x. So when we do that, thinking of our function composition from Algebra 2, we would put that 2x plus 3 in for the x of the original function. I'd keep that minus 1, and then I'd still have the plus 3 on the outside. Then I would clean that up, and I'd have a square root of 2x plus 2 plus 3, and this would actually create the new function with our transformations. So now we've taken a function and created some new transformations for it. What I did is I used this function right here to create this T-chart right here. So again, you could pause this and kind of think about how I got this. So you could create this T-chart using the same things that I did over here if that would help you understand it. So just kind of hold those T-charts in your mind. We're going to make reference to those here in just a moment. The questions that we're ultimately trying to ask are down here at the bottom of the page. So looking at question number 1, the question that we want is, let's say I have this point 1, 3, and it's on the graph of f of x. And if we look to our T-chart up above, sure enough, we can find this point. Okay. Remember, this first T-chart is for f of x, and the second T-chart is for the f of 2x plus 3. It's the transformed one. Okay. So keep that in mind. Now, let's say I have this first point that I can see. I want to know, how does that point, or what would that point be on the graph of 2x plus 3? So I want to know, how do I get from the point 1, 3 to the point negative 1, 3 without having to do a T-chart? So what we're going to do is we're going to look at two methods. The first method is going to be the easiest method, I think, and then the second method will help you maybe understand the first. So option 1 is what I call simple solving. Okay, if we simply take the x coordinate that we want to transform and the transformation that we want to apply, and we simply set those equal to each other. So we'll have our 2x plus 3, and we set that equal to a 1. We can go ahead and we can solve that. And sure enough, we get that new x coordinate that we wanted. And since there were no vertical transformations on here, the original y coordinate can stay the same. So our new point is negative 1, 3, which is exactly what we were expecting from our T-chart up above. Now, the reason that this works is because what's necessary when we are doing these problems is to understand that the transformations needed to be done in this very specific order: the dilation, a reflection, and then a translation. The problem with trying to just do them the way they're currently written is when we look at the transformation that I have here, this 2x plus 3, the dilation and the shift are mixed together. So what we really need to understand is how much was the dilation and what was the shift. And the way we would get that would be to factor this out. So I'm going to use a bracket here actually because it's going to help me see this a little bit better. I'm going to factor out the dilation, that 2, and then I'm going to get an x plus 3/2. This allows us to be able to understand the dilation and then the translation, and it separates them. If we do this working piece by piece, following this order, dilation, reflection, translate, we will get the same answer. So let's take our original 1, okay? So that was the original ordered pair that I wanted to translate. And I have this dilation of 2. And on the previous video, I talked about the fact that this 2 means that we're moving twice as fast. So we're going to finish in half the time. So what we actually do is we take that 1 and we divide it by the 2. So I'm going to think instead multiply by 1/2 because multiplication is easier. So that gets me a new x coordinate of 1/2. Now I'm going to take that 1/2 and I'm going to do the shift. Now this was a plus 3, which means that really I'm moving to the left, or plus 3/2, which means I'm really going to move to the left 3/2. So now I'm going to take that 1/2 and I'm going to add to that a negative 3/2. And that's going to get me a negative 2/2, which of course gets me the -1 that I wanted. And sure enough, there's the same ordered pair. Now, most students, when they're working with horizontal dilations and horizontal shifts, would not go through this whole process separately. They would do the simple solving. That's much, much easier. When we're talking about our vertical shifts, we are going to use that DRT only because it's just very easy. Vertical shifts appear exactly as they are. So let's take a look at that example. Okay, so if we take a look then here at example number 2, I have the same point, 1, 3. Okay, so I'm working with the exact same ordered pair here, 1, 3. I already know what's going to happen for the 2x plus 3. In the previous step, we saw that the 1 was going to become a -1. But what we want to know now is what's going to happen to the 3 when I apply the 5 and the 4. Okay, now we're going to actually follow that DRT. So we're thinking DRT, dilation, reflect, translate. So I'm going to take the 3 and I'm going to apply the dilation first, and vertical dilations can be read exactly as they are. So I just take the 3 and I multiply it by a 5, and that's going to give me a 15. Then I'm going to do the shift, and I'm going to just add that 4, and that's going to give me a 19. So now, if I wanted to apply both the vertical and the horizontal and all of this crazy business, my final ordered pair would be a -1 from the previous problem, and then a 19 for the verticals. So let's just try one more with the x's, because the x's are always more complicated. So we are going to transform the 50, and we're going to apply the 2x plus 3. We don't have to do anything to the 10. So all we have to do is take the, let me erase that there, sorry. All we have to do is take the 2x plus 3, and we're going to set that equal to the 50. So that gives me 2x equals 47, which gives me a new x coordinate of 47/2. So my transformed point is 47/2, comma 10, because I didn't do anything to the y coordinates. Okay? So We'll do a whole lot more practice. If you have my note guides, I have a whole page of these where you can just practice making sure that you can do the horizontal and the verticals.